Welcome to the shape of space, linear algebra, vector spaces. In this lesson, we're going to talk about the definition of vector spaces, several examples, and then we have one theorem at the end of this lesson. So let's start with a high-level definition of a vector space, then we'll get into the details on the next couple of slides. So fundamentally, a vector space is a set that has two operations. One called addition, it lets you add the vectors together, and the other operation is scalar multiplication, which lets you multiply a number times your vector, which makes the vector either longer or shorter. The two operations have to fulfill a number of axioms, and that's the actual definition that we'll talk about on the next slide and the slide after that. Real vector spaces and complex vector spaces are kinds of vector spaces based on different types of scalars and vector elements, in this case real or complex numbers. You can also have scalars based on something known as a field, which is a more general structure, but for the most part we're only going to talk about real and in a few cases complex vector spaces. Let's look at the formal definition of a vector space. This is a bit abstract. As I mentioned earlier, there's a number of axioms that need to be satisfied for our set of vectors, and we'll list them here on this page and the next, and then I'll give you an example which may make it a little bit more concrete. So formally, a vector space over, for example, the real numbers consists of a set of vectors, V, along with the operations vector addition, represented by a plus sign, and scalar multiplication, where we just put the scalar next to the vector. So we use juxtaposition to indicate scalar multiplication. And the two operations must meet the following axioms. And in terms of notation, we're going to use U, V, W for the elements of our vector space, and then the scalars A, B, and the real numbers. And as I say, they could be, in some cases, in the complex numbers, and I'll mention when that happens. So we have the first four axioms out of the total of 10 axioms listed here. First one is closure. So if you add two vectors from your vector space, you should get another vector that's in your vector space. Then it's commutative. So the order of addition doesn't matter, as you see here. For any two vectors in your vector space, u plus v equals v plus u. Associative, so you can, if you have three added together, you can add the v plus the w and then add it to u, or you can add v plus u and then add w, and they should be equal. Then there's something known as the zero vector, and when you add that to any other vector in your vector space, you get back the same vector. Okay, so those are the first four axioms. We have six more, which I'll get into on the next slide. Let's continue the definition of the axioms that are required to have a vector space. The first one here at the top of the slide is additive inverse. So every vector has an additive inverse, which we write as minus v, and when you add v plus minus v, you get the zero vector. The vector space needs to be closed under scalar multiplication. So if you multiply a number a times your vector v, you get another vector in your vector space. Scalar multiplication distributes. So you can see here you have a plus b, which is the sum of two scalars, times v, and that gives you av plus bv. And then you can also distribute scalar multiplication times the sum of two vectors, and you have a times u plus v, and that equals au plus av. You have a sort of associative law for the scalars. So ab times v is the same as a times b times v. And then finally there's scalar multiplication by a identity element or a unit, and the number one times v gives you back the vector again. Okay, so these are the 10 axioms. As I say, they're a bit abstract, and I guess you may be asking, well, why do we do this? The reason we do it is there's many structures that fit this definition of a vector space. And when you go to prove theorems, and there are many theorems we can prove about vector spaces, we only want to prove them once. We don't want to prove them for the dozens of examples that fit the structure of a vector space. That's very inefficient. So that's a common pattern in mathematics. We have many different structures like groups, fields, rings, metric spaces, in this case vector spaces, that have many examples that fit the structure. And the idea is to define the basic structure, then prove theorems about the structure that apply to all the many different cases. So we'll see in the next few examples just a small number of the possible types of, or structures, I should say, that fit the description of a vector space. In terms of notation, I wanted to say a few things. This is something I'll use in this video, as well as several of the videos following on the same topic of vector spaces. So I think I mentioned before about U, V, and W being used for the for vectors. That's as best as I can. I've used that notation. And if you have more than 3, then I started using subscripting. So you see here V1 sub 1, V sub 2, V sub n. And then I tried to use the initial letters of the alphabet, A, B, and C, for scalars. And again, if we had more than 3, then I might use subscripting, like A sub 1, A sub 2, all the way up to A sub n. I'll try to state at the beginning of a theorem or a definition or a discussion what are the vectors and what are the scalars. In a few cases, there's a possibility of confusion as to what's a scalar and what's a vector, and I'll use the little arrow above the variable just to emphasize that it's a vector. I didn't need to do that too often, but it's a lot of extra typing. But when it's needed to clarify things, I did use this notation. And then the other thing I wanted to mention is there's 2 types of addition. So you can add scalars together, and you can also add vectors together. Hopefully that's clear from the context. I'll try to point it out if I think it may not be clear. And the same issue was multiplication. You can multiply a scalar times a vector to make it longer or shorter, basically scaling it, which is why the term scalar is used. And then you can multiply 2 scalars or 3 scalars together. That's just multiplying numbers together. If they're real numbers, then it's something you've already seen. If it's complex numbers, it's a little bit more involved. I don't believe I use that very often, but where I do, I'll mention that. Okay, so that's the notation. There'll be other notations, but these are some of the basic ones that I wanted to mention. So we have our first example here. This is the real plane, XY axis. Hopefully you've seen that, and even in high school algebra. So it's the R2 is how we describe, or the notation for the real Euclidean plane. And then it's over the field of real numbers. So the scalars are real numbers. So we have the definition here. The real plane, the set R2, all the ordered pairs x, y, where x and y are real numbers, is a vector space over the real numbers. And we define addition point by point, or component by component. So you see here we have 2 vectors in our vector space, and when we add them, we just add the x's, the first components together, and then the second components together. And of course, this is also an element of this set. So we've already effectively defined this, so we have closure. And then scalar multiplication is even easier. You have a real number a times an ordered pair x, y. You just multiply a times each of the elements. And again, this is another ordered pair. So we've proven closure for scalar multiplication. We'll hit that a second time when we go through the axioms. So the first one is closure for addition. That's pretty obvious when I just mentioned that one. And then the second one is the commutativity. So if you have two elements from our vector space, you add them together, then what you have in each component here are just real numbers. So we know the real numbers are commutative under addition, so we can just switch the x1 and x2 and the y1 and the y2, and then this is by definition x2 y2 plus x1 y1. So it's the opposite order that we started with. So that proves the commutative property for our example vector space. We have a few more of the axioms on this slide, and it'll carry on to the slide after. So the associative law for our vector space depends heavily on the associative law for real numbers, as did the previous axiom on commutativity. So we take three vectors in our vector space, and we have two of them grouped together. We add those first, as we see here. Let me point to, so these two here, we add together first. Then we have now two vectors, and we add those together. So we have this expression here. And then what we have inside here are just real numbers, and we use the associative property of real numbers to regroup them, as you see here on the right. Then we break it into two pieces based on the definition of our sum or addition for our vector space. And then we just have the grouping. We break this again into a sum. So these are grouped together. So you notice going from here to here, we've proven the associative law. And the key step was in here, going from here to here. And that was depending on the associative property for real numbers. Then the zero vector is pretty simple. It's just the ordered pair 0, 0. When you add that to any element from our vector space, x, y plus 0, 0, gives us x plus 0, y plus 0. But again, these are real numbers. And we know 0 plus any real number is the number itself. So we just get x, y. The additive inverse is equally easy. We just take the negative of each component of our vector x, y. So we have x, y plus minus x minus y. We get x minus x, y minus y, but these are real numbers. And we know that when you have a real number minus itself, it's 0. And so we get 0, 0. In terms of multiplicative closure, when we multiply by a scalar, we have a times a vector xy. By definition, that's ax, ay, but then this is just the product of two numbers, two real numbers, and so is the second component here. So again, this is an element of our vector space. Then we have these distributive laws, which follow pretty much from the distributive laws of real numbers. Let's see the first one here. So we have a plus b times the vector x, y. A and b are real numbers. Then by definition, it's a plus b times x is the first component. A plus b times y is the second. Then we expand this out. This is just the distributive law for real numbers here and here. And then we can break this into two pieces, again, using the definition of vector addition. We get this, and then we can, again, use the definition of scalar multiplication to pull the a and the b out. We get this here. So we have a plus b times xy equals a times xy plus b times xy. You have a similar thing down here. In this case, we have a scalar times the sum of two vectors. We use the definition of vector addition to get from here to here. And then we multiply a times each term. Again, that's the definition of scalar multiplication. Then we use the distributive law of real numbers to go from this step to this step. We get this here. Then we use the definition of vector addition to just break this into two vectors. And then we use the definition of scalar multiplication times a vector to pull the a out of this term and the a out of this term. And as you can see, we have the property a times the sum of two vectors is a times the first vector plus a times the second vector. We're almost done. We just have two more. Again, we're using the definitions from real numbers to prove these. So we have ab times the vector xy. Using the definition of scalar multiplication, it's ab times x, ab times y. But then from the property of associative law, for real numbers, we have a times bx, a times by to get from here to here. Then we can pull out the a using the definition of scalar multiplication times a vector. And we can pull out the b, again using that same law. And then we have the property that we wanted. Finally, 1, the real number 1 times xy equals 1 times x, 1 times y. But since 1 times the real number is the real number itself, we just get xy. So there we have it. Going through all 10 of the axioms, we've proven that two-dimensional Euclidean space over the real numbers is a vector space. We can extend our previous example where instead of having just two components, we have n components in our vector made up of real numbers. So you see here we have the set R superscript n, which is the set of all n tuples, where each of the n components is a real number. Then we define addition pairwise. So we just take the first components and add those, and then the second, and all the way up to the nth components. And then scalar multiplication is just taking the scalar a and multiplying it times each element. So this is a vector space. I won't go through the details again. It looks very similar to what we did for the previous examples, just a little bit more tedious given that you have now n components to each vector. And in fact, you can actually have an infinite number of components, and that's called R superscript infinity, and that would be an infinite dimensional vector space. And we would define addition and scalar multiplication in a similar way. And just one other point to be made here, R superscript n is formed as a Cartesian product of n copies of R. We write that as R superscript n equals R times R times R, and it's basically this set here, which we've defined up here. So more of a notational thing. I'll use this occasionally in some of the other examples where you just take a given set and then you take the cross product, the Cartesian product, of multiple elements of that to get another set. We can try a few variations to our previous example. The first one you might want to try is taking the n-dimensional Euclidean space, Rn, over the complex numbers. And that's not going to work because when you multiply an element from Rn by a complex number, you're not going to get another vector in Rn. You're going to get a complex vector. So this extension is not valid, but there's two others that are valid. We can take n-dimensional complex space, which I represent here as c to the n, over the real numbers, and that's the vector space. So the scalars are real numbers, but when you multiply a vector comprised of complex numbers by a real number, you still get another complex vector. And the other possibility is taking the n-dimensional complex space over the complex numbers, and that also works. So these two are not the same, but they are both valid vector spaces. Example number 3, it's the set of all multiples of a constant vector in Rn. So consider the set L of all real scalar multiples of a vector, constant vector, which we'll call W, and it has n components. It's an element of Rn. And the claim is L is a vector space. And more precisely, it's a subspace of Rn, but we haven't defined subspace yet. We'll get to that in the next video. So we need to check the axioms. First try for closure, we take U and V and L, which means that U is a multiple of W, AW here, and V is a multiple of W. Then we add U plus V. We substitute in AW and BW for U and V. Then we use the distributive law here to factor out W, and the distributive law holds because L is a subset of Rn. So we have shown closure because this is A plus B is just the constant times W, and then by definition that's an L. So most of these properties are going to hold because L is a subset of Rn. The commutative law under addition and the associative law under addition both hold because L is a subset of Rn. If you take 0 times W, you get the 0 vector, which is in L now because it's equal to 0 times W. Notice this 0 here is a scalar and this is a vector. So I put the little vector symbol on top of the 0 just to make clear the distinction. If U equals AW is an element of L, then we can just take minus AW, which is the additive inverse of AW, and I kind of proved it here where you factor the W out and you get A minus A, which is 0. This is just two real numbers subtracted from each other. That's 0 times W, which equals 0. So the additive inverse law holds. If you take a element of L, which is of the form AW, then we can multiply that by any scalar. Using the distributive law here, we get BA times W, and then again, that's just a multiple of W, so that's also an L. So we have closure by scalar multiple. Then a number of these are, again, inherited. The scalar distributive law, the vector distributive law, they both are inherited from Rn. Scalar associativity is inherited. The unit vector is inherited from Rn. So we have that. And as I mentioned at the beginning of this, L is essentially a straight line. It follows the path, or it's in the direction of our vector W that we chose to define L, and it goes through the origin. That's because of the way we defined L, that 0 times our vector W is the 0 vector, and so it's basically a straight line going through the point 0, 0 n times. We have a couple more examples of vector spaces on this slide. The first one is the set of polynomials of order n minus 1. So we have it here, the set P sub n, and it's all the polynomials of this form here going all the way up to the power n minus 1. And then we add these by just adding like terms corresponding to similar powers. And we multiply by a constant just by multiplying the polynomial by a constant. So you should have seen this in high school algebra, maybe not to the n power, but just in general. You know that when you add polynomials, you add the coefficients of the same power, and you can just multiply by a constant. You do that when you work with a system of linear equations. So it looks almost exactly like the Rn. We have n coefficients going from 0 to n minus 1 in this case, and the addition and scalar multiplication looks almost the same. In fact, Pn is what's called isomorphic to Rn. We'll talk about that several videos in the future, but it's basically isomorphic. In fact, it's even more, we can say even more than that. All finite dimensional vector spaces of the same dimension are isomorphic. They basically have the same properties as far as vector spaces. Then the second example we have here, again, is similar to Rn. If you just take the matrices, m by n, for example, then that's also a vector space. We add, just the way I showed in the first video from this series, you add them by adding terms in the same position, and then you can multiply the entire matrix by a scalar. So it looks very much like Rmn, because you have m times n entries in your matrix in this vector space, and this would be isomorphic to Rmn. So again, it's a vector space. You may want to go through and check some of the properties, but some of the axioms, but you'll find that they all hold true. Consider this set f of all functions from the natural numbers n, that's the numbers 1, 2, 3, 4, 5, etc., to the real numbers. This is a vector space under the usual operations for function addition and multiplication by a scalar. I'll leave it as an exercise for you to check the axioms. Just give you maybe one example. The zero vector would be f of n, and taking the natural number as its input, mapped to 0 for every value of the natural numbers. So let's look at a particular element from this set, f of n equals n squared plus pi. We could represent that by this table here. N equals 1 gets mapped to pi, n equals 2 gets mapped to 4 plus pi, and so on. And you can see the function itself looks like an infinite dimensional vector in our vector space R infinity, which we talked about earlier. And in fact, f is isomorphic to R infinity, and this is just one such element. So going a little bit further, if we let this function, if we represent this function here, this particular function, as v sub f, and we write it as this infinite sequence, infinite n tuple, then the set of all scalar multiples of v sub f is a subspace of our vector space f. It's basically a straight line in infinite dimensional space, or it's equivalent to a straight line in infinite dimensional space. Okay, so this one's a little bit different from what we've seen up until here, but again, it's another example of a vector space, and then here we have a subspace. We have one more example. That's the example of the solution set to a homogeneous linear system. I have it written here, AX equals 0. So A is a matrix. It doesn't have to be square. And X is a vector, a column vector, and it has n variables. And then 0 is also a vector. So we get a set of equations from this matrix equation. And the set of solutions I claim is a vector space. It's pretty easy to show that. Let's just look at a more concise definition of what we're talking about here. The set of solutions is the set S of vectors X, where X has n components, so it's an element of R sub n, such that A times X equals 0. So we'll just show a few of the axioms. If we have two members of this set, U and V, then AU equals 0 and AV equals 0. And if we look at A times U plus V, just from matrix multiplication, we get AU plus AV, and these each equal 0. And then when you add the two 0 vectors together, you get 0. So in other words, u plus v is an element of S if u and v are an element of S. So that's additive closure. We could do the same thing with multiplicative closure, scalar multiplicative closure. So if we take u and S and some real number alpha, then we evaluate a times the scalar alpha times u, and we can pull the alpha out here to the left times au, and then au of course is 0, and then a scalar times 0 is again the 0 vector. So alpha times u is also an S. So this is closure on the scalar multiplication. Yeah, the 0 vector is always a solution. There's a few more to check, another 7 to check, but most of them are not difficult. So I'll leave that as an exercise. One thing I wanted to point out, and it's a little bit beyond what we've discussed in terms of theory so far, but this system may have only one solution to x equals 0. And the criteria is that the columns of A need to be dependent in order to have more than one solution. Dependent means just a column, one column of A can be written as a combination of the other columns. That would say that they're dependent, in which case the system here, AX equals 0, would have multiple solutions. If the column vectors of A are independent, in other words, you can't write one in terms of the other, then there is in fact only one solution, which makes this not a particularly interesting problem in that case. We conclude this lecture with a theorem. I've probably used these identities here a few times without proving them in the examples that we've gone through, but they do need proof. So let's look at these. We have a vector space V with a vector small v in V and a scalar A in the real numbers. Could be any field over which the vector space is defined, but we'll just focus on the real numbers here. So we have three identities: 0 scalar times v equals a 0 vector, minus 1 times v plus v equals 0. In other words, minus 1 times v is the inverse of v. And then the scalar, any scalar times the 0 vector, is the 0 vector. So the first one is a bit involved, surprisingly. It looks kind of obvious. You would expect this to be true, but it takes a little bit of effort. So we have v equals 1 times v by definition. Then we can write 1 as 1 plus 0 and times v. And then we use the distributive law, and we get 1 times v plus 0 times v. And then we assume u is the additive inverse of v. We know that exists because capital V is a vector space. And we add u to both sides of this. We get this expression here. Then since u is the inverse of v, this is 0, this is 0. And then 0 vector plus any vector is the vector itself. And then we have 0 times the 0 scalar times v equals a 0 vector. So that's the first one. The second one, we have minus 1 times v plus v. And then we just, going from here to here, we write v as 1 times v. That's from the identity, multiplicative identity property for a vector space. Then we use the distributive law to factor the v out. And these are just real numbers, minus 1 plus 1. So they equal 0. And then you have 0 times v. And then we've proven in the previous identity, that this is the 0 vector. So that gives us the second one. Then the third one, we have scalar times the 0 vector. And we can write the 0 vector as 0 times the 0 vector from just reusing this here. And then using the distributive law, this is the same as a times 0 times the 0 vector. But a times 0, these are two real numbers, so it's just 0. And then again, using this property, 0 times the 0 vector is the zero vector. So a scalar times the zero vector is always the scalar vector. Okay, so that was it for this lesson. The next lesson's on subspaces, subspaces of a vector space.